Hey, so I'm gonna start a little series on symmetry, um, specifically the symmetry of inorganic molecules because I thought that was pretty fun in undergrad. Well, not at the beginning, but towards the end and the middle, yeah. So yeah, today we're going to talk about how you determine your um, proper or major rotation axis of your inorganic molecule of choice. So, why is symmetry important just in general? I mean, like molecularly, I know that we think of symmetry as just like, oh, like their face is symmetrical, whatever, or like you see symmetry in nature a lot, like snowflakes are symmetrical, a lot of plants are symmetrical, they grow out like radially and they just like are congruent. And like animals' patterns have symmetry and like blah 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 blah. The thing is with that kind of stuff, like yes, a lot of stuff is symmetrical and like beautiful and what have you, but that kind of symmetry usually doesn't tell you fundamental principles about something or how something would react or, you know. But whenever you look at the symmetry of like molecules, so symmetry on a molecular scale, that can tell you a lot. So like symmetry can tell you if a molecule is polar or not. You can use symmetry to predict spectra, like Raman spectroscopy. So you can predict the vibrational energies of a molecule using symmetry. You can also apply symmetry to crystal field theory, which is really cool and fun, and ligand field theory and a bunch of other stuff. So yeah, cool stuff. I think the first thing to kind of differentiate would be what is the difference between a symmetry element and a symmetry operation. So a symmetry element is like a geometric entity. It's like a point, a line, or a plane, but it is a point, a line, or a plane about which a symmetry operation can be performed. So you perform your symmetry operations on a symmetry element. Today, we are going to be defining your major rotation axis of your molecule. So we're going to be defining a key symmetry element about which you can perform symmetry operations, okay? So a symmetry operation, moreover, is like the action or movement that I was talking about, that when you're carrying your chemical species from an initial position or orientation to an equivalent position or orientation about a symmetry element or axis. Yeah. So we're going to start out with an example. Something to keep in mind whenever you're doing this is that you need to be well versed in how to draw Lewis structures, and you also need to be well versed in understanding the geometric shape of your molecule from the Lewis structure you have drawn in order to determine your proper rotation axis of your molecule. So I have my old whiteboard. Okay, so we're gonna start with an example. Let's do boron trihydride. So BH3, okay? Once again, you need to know how to do your Lewis structures. That's just, you have to know. So boron has 3 valence electrons, okay? Hydrogen, we have 3 of them, okay? And then each hydrogen has 1 valence electron, okay? So we need to account for 3 valence electrons for the hydrogen and 3 valence electrons for the boron. So with a total of 6 valence electrons in our Lewis structure. A common like rule of thumb, I don't know who's going to be watching this, if you are well versed in chemistry or whatever, but usually that first atom is going to be in the center of your Lewis structure for like most small molecules. I know sometimes that might not be the case. You could have like a hydrogen up there, and hydrogen like it is an acid or something, or there could just be a hydrogen at the beginning of a molecule for whatever reason, but that obviously wouldn't be the center. But I think a common rule of thumb is that the first atom presented in your structure or in your formula is going to be in the center of your structure. And that is the case with boron trihydride. So I'm just going to draw my boron down here. Okay, we need to use up our 6 valence electrons. Okay, so we have 3 hydrogens. I'm just going to like put them in space. So a line or a bond between atoms is going to be representative of a covalent bond, and so each of those bonds is representative of 2 valence electrons. Okay, so I need to join boron to 3 hydrogens, so I'm just going to put 3 bonds. Easy enough. So 3 bonds, each one is 2 electrons. That's 6 electrons. We've used up our electrons. This is our structure. Okay, so what is a proper rotation axis? I'm glad you asked. Like where do we begin? Okay, so a proper rotation axis uses this nomenclature. So we have C and then subscript N. What is N? Okay, N is equal to 360 degrees divided by your angle of rotation. Okay, that is what N is. Okay, so your angle of rotation, yes. So you're going to be rotating your molecule. I think it's important to highlight this here, 360 degrees. For this example, I'm just going to put a circle around my molecule. How many degrees are in a circle? 360, good job. So based on this Lewis structure, its shape is trigonal planar, okay? By like definition, the distance between bonds of a trigonal planar structure is 120 degrees. Okay, so each of these distances is going to be 120 degrees. My proper or major rotation axis for that, I'm going to, there's a fly. I'm going to put a line through the center of my molecule, an imaginary line. Okay, so act like there's this line that's going through the board, through the boron, okay? And I'm able to manipulate this molecule by grabbing the top of that line and rotating the molecule around, okay? I want to rotate this molecule through this axis enough so that I can rotate it and the molecule looks exactly the same as it did when I started, but not enough rotation so that it just goes all the way back around to 360 degrees, okay? That is called, the identity is just like the exact same thing, like you're literally rotating it all the way around, that's your identity. I want to pick something smaller, a shorter distance, okay? So there's 3 equal 120 degree distances between these bonds. If I take my line that's going through the board and I rotate this 120 degrees, what's the molecule going to look like? It's going to look exactly the same. So, but I can't move it 60 degrees. Like if I moved it here, it would not look like how it does right now. I need to move it so that this hydrogen is going to be in the spot of this hydrogen, and they're each going to be moved around so that it looks exactly the way it does right here. Because if I rotated this molecule 120 degrees, you wouldn't be able to tell the difference, okay? So 120 degrees is my angle of rotation for this molecule. Then we go back up here. N equals 360 degrees divided by my angle of rotation. If my angle of rotation is 120 degrees, N equals 360 divided by 120. So N equals 3. So this molecule, we know it has a C3 axis, okay? The C3 axis is going straight through the boron, okay? But it's important that you don't just stop there, because molecules can have more than one type of rotation axes, okay? So something that is important, once you've found all the axes that a molecule contains, you want to pick the highest order axis to be your proper or major rotation axis, okay? So if that ends up being C5, C4, whatever, if it's the top number, the highest order in, then that's your major rotation axis. So let's look at this molecule from a different perspective. We know that it's a flat molecule, okay? So that means that we could, like, imagine this marker is my molecule, and right now it's like this. Let's like take it up into 3D space and look at it down one of the hydrogens. So we're gonna look down a hydrogen boron bond at the molecule still flat, but this way, okay? So we're taking it like this, okay, looking down a bond. Is there any way that we can rotate this molecule down this bond? So I'm putting my imaginary line through the hydrogen boron bond out into space, okay? Is there any way we can rotate that so that we're rotating it less than 360 degrees, but we still end up with the exact same looking molecule? The answer is yes. So if we rotate it 180 degrees, so just flip it upside down, it's gonna give you the same molecule. You're just flipping two of those hydrogens. You're switching their places, okay? So 360 divided by 180 is 2. So we know that there are C2 axes in BH3 as well. But as I said earlier, you want your proper rotation axis to be the axis of highest order. So 3 is greater than 2. So for our symmetry operations, we're going to use the C3 axis for boron trihydride instead of any of the C2 axes. I hope that makes sense. Okay, so let's do another example. Let's do xenon tetrafluoride, okay? So, XeF4, okay? As always, we're gonna draw our Lewis structure. So, xenon has 8 valence electrons, and then fluorine, there are 4 of them, so we're going to multiply by a factor of 4. And so fluorine's a halogen. Halogens have 7 valence electrons, okay? So 8 electrons from our xenon, and then 28 electrons from all of our fluorines combined will give us 36 total electrons that we need to represent in our final Lewis structure, okay? So I'm going to go ahead and just draw it like I did the other time. Xenon is going to be our central atom. I'm just going to draw the 4 fluorines out here. I'm going to go ahead and form a covalent bond from each fluorine to the xenon. Okay, so we just used 8 of our valence electrons that we needed to, because each bond, as I said before, is representative of 2 valence electrons. Okay, so we just knocked that down to 28 electrons. Okay, so the thing with, I mean, all atoms, whatever, but like halogens, their valence is 7. Okay, and so in order to make the halogen have just a formal net neutral, or like a formal charge of 0, then we're just going to put 3 lone pairs on each fluorine. Okay, so fluorine's valence is 7. In order to determine formal charge, you can do valence minus the number of electrons that are not part of a bond, and then minus the number of bonds. So fluorine, that would be 7 minus 6 electrons that are unbound on the atom, and then 1 bond. So that would give it, all of these, a formal charge of 0. But we are left with, let's see, so we have used 32 electrons, so we're left with 4 extra. Where are they going to go? So we're going to put 2 lone pairs on the xenon, and this will be our final structure. Okay, so what makes this molecule different than the last one that we did? I'll show you. So once again, we want to find the proper rotation axes for this molecule, xenon tetrafluoride. As I said before, we want to know what N is. So N is equal to 360 degrees divided by your angle of rotation. Okay, so where are we going to start? Let's see. So I think a good rule of thumb, or how I usually do it, is like this molecule is like flat like this. Specifically, this is a square planar molecule, square planar complex, so each of these is separated by 90 degrees. So I'm going to put an axis right here through the xenon. Okay, so I'm going to put a line through the xenon. And I want to know what is the shortest distance I can rotate this molecule so that it looks exactly the same as when I start, as to when, like after I've done the rotation, without going 360 degrees around and just making the same molecule. Okay, so if I rotate it 45 degrees, fluorine's gonna be right here. That is not the same at all. If I rotate it like 60 degrees, no. So it's good to just go the length of the bond angle. Okay, so if I move this down and rotate this molecule 90 degrees, this fluorine's now here, this fluorine's now here, this fluorine's now here, and this fluorine's now here. The molecule looks exactly the same. I rotated it 90 degrees. 360 divided by 90 equals 4. So we know that this molecule has a C4 axis, okay? But once again, they could always have more. And you need to figure out if C4 is the highest rotation axis that you can find. Because if it's not, then you need to pick the other one that's higher. So let's look at this molecule. So as before, whenever I did it with the boron trihydride, let's take this molecule out of this plane and bring it up flat in front of you, okay? So we're gonna be looking down these fluorine xenon bonds, okay? So I'm gonna take one of these and act like this is my molecule. I'm putting a rotation axis, a line through the fluorine xenon and out through the other fluorine, like this, but in front of me. Can I rotate it in such a way that the molecule is exactly the same without rotating it a full 360 degrees? Yes, I can rotate it 180 degrees. And so 360 divided by 180 is 2. So I know that there's a C2. So I can look down the axis through this way, but I can also look this way. So there are 2 C2s that are like on axis, like this straight line. But you can also take the molecule in front of you and go down these diagonals. Okay, so you can look at it diagonally this way, flip it 180 degrees, same molecule. You can take a diagonal this way, flip it 180 degrees, same molecule. So there are also 2 C2s that are diagonal across the molecule this way. Okay. Let's see. Yeah, so I don't really want to do another one. That was fun. If someone watches this and wants to see more, I can do more. The next thing I'm going to talk about is like mirror planes, so like reflections of molecules. And then I will go to centers of inversion, improper rotation axes, and then discerning which point group molecules should be assigned to, and then like onto character tables and more fun stuff. So, thanks for watching.